Gravity is a force. It pulls the apple from the tree, holds the moon in orbit, keeps your feet on the ground. Newton proved it 300 years ago. And according to our deepest understanding of the universe, confirmed by precision clocks in orbit, gravitational wave detectors, and over a century of experiments, it's wrong. Gravity is not a force. If it's not, then the weight you feel right now, the most familiar sensation of your entire life, is something else entirely, something far stranger. And understanding what gravity actually is means rebuilding everything you think you know about space, time, and what it means to fall. Start with what Newton got right, because he got an extraordinary amount right. In 1687, he published the law of universal gravitation. Every mass in the universe attracts every other mass. The strength of that attraction depends on two things: how much mass the objects have and how far apart they are. Double the distance, the attraction drops to a quarter. With this single equation, Newton explained why planets trace ellipses around the sun, why the tides rise and fall twice a day, why a cannonball follows a curving arc back to Earth. Within decades, astronomers were using his law to predict planetary positions years in advance, and their predictions matched observation to extraordinary accuracy. For the first time in history, the motion of the heavens and the motion of everyday objects obeyed the same law. It was perhaps the single greatest unification in the history of science. And it left the deepest question completely unanswered. How does the sun, sitting 93 million miles away across empty vacuum, pull on the Earth? What is reaching across that void? What physical mechanism connects two masses separated by nothing? In Newton's framework, this influence was instantaneous. If the sun vanished, Earth would somehow know immediately, responding to the absence faster than light itself could carry the news. The speed of light limit hadn't been established in Newton's day, but the philosophical absurdity was already glaring. Newton himself was haunted by this. In a letter in 1693, he wrote, "That one body may act upon another at a distance through a vacuum, without the mediation of anything else, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it." The man who discovered the law of gravity called his own law absurd. Not the mathematics was perfect. The mechanism. He described gravity with extraordinary precision. He never explained it. And for over 200 years, no one could. The answer began with a daydream. In 1907, Albert Einstein was sitting at his desk in the patent office in Bern when a thought struck him, one he would later call the happiest thought of my life. He imagined a person falling from a roof. During the fall, that person would feel completely weightless. Not lighter, weightless. The identical sensation you would feel floating in deep space, far from any star or planet. Einstein realized this was more than a curiosity. It was a clue, because it meant there is no experiment you can perform inside a sealed box that will tell you whether you are freely falling near a massive object or floating in empty space with no gravity at all. The experiences aren't just similar, they are physically identical. He pushed it further. Imagine you're standing inside an elevator with no windows. The elevator is resting on the surface of the Earth, and you feel your normal weight. Your feet press the floor with a familiar force. Now, imagine the same elevator in deep space, far from any planet, but a rocket engine underneath is accelerating it upward at the same rate. You would feel exactly the same weight, pressing into the floor in exactly the same way. No instrument in the universe could distinguish between the two. This is the equivalence principle, and its implication was extraordinary. If gravity and acceleration produce truly identical experiences, if no measurement can tell them apart, then they aren't merely similar, they are the same physical phenomenon, described from two different perspectives. And if gravity is indistinguishable from acceleration, then it isn't some mysterious force reaching across empty space. It must be something about the structure of space itself, about the geometry of the arena in which everything moves. The universe had been concealing something fundamental about the nature of motion, and Einstein had caught the first glimpse of what it was hiding. It took him 8 more years of difficult mathematical work, but in 1915 Einstein published the general theory of relativity. Its central claim was breathtaking. Space and time are not separate things. They form a single 4-dimensional fabric, space-time. You exist within this fabric right now. You move through it with every passing moment. Everything does. Far from any mass, space-time is flat, and in flat space-time, the straightest possible path between 2 points is exactly what you'd expect, a straight line. An object drifting through empty space with no forces on it moves in a straight line at a constant speed. On this, Newton and Einstein agree completely. But mass changes the fabric. A massive object like the Earth doesn't reach out and pull on nearby things. It warps the space-time around it, curving the geometry. Picture a heavy ball resting on a stretched rubber sheet. The sheet sags, and the geometry near the ball is different from the geometry far away. A marble rolling across the sheet curves toward the ball, not because the ball pulls it, but because the surface it's rolling on is no longer flat. Now extend that picture to 4 dimensions. Near a massive object, the straightest possible path through space-time, what physicists call a geodesic, is no longer a straight line. It's a curve. And this is gravity's true identity. Objects in curved space-time aren't being pulled by any force. They are following the straightest available path through warped geometry. The moon orbiting the Earth isn't being tugged sideways by an invisible rope. From the moon's own frame of reference, it is travelling in a straight line through curved space-time, and that straight line happens to loop back around. No force, no mysterious action at a distance, no instantaneous signals across the void, just geometry, reshaped by mass. This was Einstein's answer to the question that haunted Newton. Mass doesn't project some invisible influence across a vacuum. Mass reshapes the stage itself, and everything on that stage, light, planets, time itself, responds to the new shape. Newton asked how gravity reaches across empty space. Einstein's answer was that it doesn't need to. The space is already curved. But this raises a question that cuts even deeper. If gravity is curved geometry, objects following bent paths through space-time, then why does something at rest begin to fall? Hold a ball in your hand, release it, and it drops. It wasn't moving. Nothing pushed it. If there's no force, what sets it in motion? This is where the picture becomes truly extraordinary, and where a framing articulated by the physicist Brian Greene reveals what may be the deepest insight in all of general relativity. Nothing is ever truly at rest. Even when you are sitting perfectly still, not moving through space at all, you are moving through time. 1 second passes, then the next. That's motion, not through the 3 dimensions of space, but through the time dimension of space-time. Here is the critical insight. According to relativity, every object's combined speed through space and time is always the same value. Always. That value is the speed of light. When you're sitting still in space, all of that motion is directed purely through time. You are moving through the time dimension at the speed of light. If you begin to move through space, some of that fixed motion redirects away from time and into space. This is why moving clocks run slower, a phenomenon called time dilation. Speed through space comes at the expense of speed through time. The total never changes. Now apply this to gravity. Mass warps space-time. Specifically, near a massive object, the direction of time tilts slightly toward the mass. Your motion through time, which was carrying you straight forward into the future, acquires a tiny spatial component pointing toward the massive object. You begin to drift toward it. That drift is gravity. That gentle tilt of the time direction is why the apple falls, why the moon orbits, why galaxies cluster. Nothing pushed the ball when you released it. The direction of forward in time was already bent toward the Earth. The ball was always going to follow. The force you felt your entire life isn't a pull. It's the shape of time near mass, redirecting your constant motion through space-time into what you've always called falling. So, if falling is the natural state, if no force acts on a falling object, then what is the weight you feel right now? Here is the inversion that rewrites your intuition. In general relativity, an object in freefall is in its most natural state. No force acts on it. It's following a geodesic, the straightest path through curved space-time. A skydiver before the parachute opens, astronauts aboard the International Space Station, a dropped coin the instant it leaves your fingers. None of them experience any force. They are doing exactly what space-time's geometry demands. You, sitting in your chair, are the one experiencing a force. The only real one in this picture. The electromagnetic bonds between the atoms of your chair are pushing upward against you right now, preventing you from following your natural geodesic, which would carry you straight toward the center of the Earth. The weight you feel isn't gravity pulling you down, it's the chair pushing you up, blocking your natural path through curved space-time. This is why astronauts on the space station float. They aren't in zero gravity. The station orbits just 400 kilometers above Earth's surface, where gravity is roughly 90% as strong as it is on the ground. What they're in is zero force. Nothing is blocking their natural path. They are in free fall around the Earth, and free fall, true unimpeded gravitational motion, feels like nothing at all. You cannot feel gravity. What you feel is everything else resisting it. This isn't a philosophical reinterpretation, it's the most precisely tested framework in the history of science. Start with your phone's GPS. Every satellite in the GPS constellation orbits roughly 20,000 kilometers above the Earth, where space-time is slightly less curved than at the surface. Time runs faster up there, a direct consequence of Einstein's geometry. The difference is tiny, 38 microseconds per day, but GPS locates your position by comparing the precise arrival times of signals from multiple satellites, and a 38 microsecond daily error would accumulate into a positioning drift of roughly 10 kilometers within 24 hours. Every GPS chip in the world applies corrections derived directly from general relativity. Without Einstein's curved space-time, your phone couldn't find the street you're standing on. Even before GPS, the theory had already proven itself. Newton's gravity predicted Mercury's orbital path almost perfectly, but not quite. The closest point of Mercury's orbit to the Sun shifts slightly with each revolution, a slow rotation of the entire ellipse. The observed rate of that shift exceeded Newton's prediction by a tiny amount, 43 arcseconds per century, roughly 1/100th of a degree. A minuscule discrepancy, but one that had baffled astronomers for over 50 years. When Einstein applied general relativity to Mercury's orbit, the equation produced exactly 43 arcseconds. No adjustments, no free parameters, just the geometry of curved spacetime around the Sun. Then there's gravitational lensing.
Light from distant galaxies passes near massive objects on its way to us and bends, not because gravity pulls on photons, which have no mass, but because the space-time the light travels through is curved. We don't just infer this, we can see it. The Hubble Space Telescope has photographed distant galaxies smeared into arcs and rings by the warped geometry around foreground galaxy clusters. We are literally photographing curved space-time. And in 2015, the LIGO Observatory detected something never before directly measured: a gravitational wave. Two black holes spiralling into each other over 1 billion light-years away sent a ripple through the fabric of space-time itself, a physical oscillation in the distance between points, stretching and compressing space as it passed through. The signal matched general relativity's prediction with remarkable precision. The fabric is real. It ripples. It bends. And we've measured it. This is also why gravity remains the deepest puzzle in fundamental physics. We know of 4 fundamental interactions. Electromagnetism is carried by photons. The strong nuclear force, which binds atomic nuclei, is carried by particles called gluons. The weak nuclear force, responsible for certain kinds of radioactive decay, is carried by W and Z bosons. All 3 are genuine forces, transmitted by particles operating within the arena of space-time. Gravity doesn't fit. It isn't a force operating within space-time. It is space-time, the shape and curvature of the arena itself. This is the deep reason physicists have spent over a century trying and failing to write a quantum theory of gravity. Quantum mechanics describes the other 3 interactions as exchanges of particles bouncing between objects inside a fixed background of space and time. But gravity is that background. Trying to describe it in the same language is like trying to paint the canvas using only the paint that sits on top of it. The hypothetical graviton, a particle that would carry gravity the way a photon carries electromagnetism, has never been detected, and there's a genuine open question about whether searching for one even makes sense. Gravity may not be the kind of phenomenon that has a carrier. It may simply be geometry, all the way down. Gravity is a force. Newton proved it. That's what we were all taught. But Newton himself called that explanation an absurdity, and Einstein showed why. Mass doesn't reach across empty space and pull. Mass reshapes space and time, curving the fabric through which everything moves. The moon doesn't orbit because Earth tugs on it. It follows the straightest path the geometry allows, and that path loops back around. And you?
Right now, every atom in your body is trying to follow its natural trajectory through curved space-time, a path that would carry you in freefall toward the center of the Earth. The only thing stopping you is the chair beneath you, its atoms pressing upward against yours, electromagnetic forces holding you in place against the geometry of the universe. The sensation of weight, the one physical experience that has accompanied every moment of your conscious life, is not gravity reaching for you. It is the resistance. You are moving through space-time at the speed of light, right now, in this moment. Most of that motion carries you forward through time, but the Earth's mass has tilted the direction of time barely toward itself, and that tilt is all gravity ever was. Not a force reaching across the void, not a mysterious pull with no mechanism. The shape of reality, bending your path through time itself. Newton gave us the description. Einstein gave us the explanation.
Brian Greene's framing strips it to its deepest layer. Everything moves through space-time at the speed of light. Mass tilts the direction, and that tilt is gravity. The answer to why mass creates gravity is that mass doesn't create a force at all. It creates geometry. It reshapes the one thing more fundamental than matter, the space-time everything exists within. 3 centuries to close the gap Newton left open, and the answer was that the most familiar sensation of your life was never what it seemed. Gravity was never a force. It was always the shape of reality. And you were always falling through it.
For a limited time only, we are giving out the first 3 chapters of our complete introduction to stargazing completely free. Check our page info for the link.